All right, so we've talked about some of the different applications to the conic sections that we've been looking at. We want to pick up then on the bottom of page 726 with classifications of conic sections by the discriminant. Now, we've already looked at how we can classify our conic sections if they don't have a BXY term, right? Back on page 719, we were looking at that in the last section, where if you don't have this BXY term, if it just goes AX squared plus CY squared, that was where we looked at A and C, right? If you multiplied A times C and you got a positive number and A was not equal to C, then you had an ellipse. If you had a positive number and A was equal to C, then you had a circle. If you multiplied A times C and you got a negative number, you had a hyperbola. If you multiplied A times C and you got 0, you had a parabola. That is when I do not have a BXY term. So what happens if I do have a BXY term in my equation? Then I'm going to use the discriminant. Remember the discriminant? B squared minus 4AC, that's what's underneath the square root in the quadratic formula. All right, I'm going to use the discriminant. And for the discriminant, if I get a negative answer, that means that my conic is either an ellipse or a circle. I don't know which. And unless I graph it, I'm not going to be able to tell which one. There is no thing like, well, if A is equal to C, then it must be a circle. That's not necessarily true. So I literally will just leave my answer ellipse or circle because I don't know which one it is unless I graph it. If I get 0, it is still a parabola. And if I get a positive answer, then it's going to be a hyperbola. Now, you'll notice that these two have pretty much switched places, right? Like it was when you got a negative answer, it was a hyperbola, and now when you get a positive answer, it's a hyperbola. An easy way to keep that straight is to think about this subtraction sign right here in the middle of the discriminant. Think of that as like the opposite of, because subtraction is the opposite of. So if I think of this as the opposite of A times C, then that'll help me remember, okay, when I did A times C and I got a negative answer, it was a hyperbola. But in this one, it's the opposite of that. So when I get a positive answer, it's a hyperbola. Also remember that you've got your 3x5 card. You're welcome to list both of those classification systems on it, so you don't have to memorize it. So look at example 4. If I'm looking at example number 4 and I want to use the discriminant, I need A, B, and C. So what is A? 2. What's B? Negative 3, yes. And what's C? Positive 2. So if I do my discriminant, B squared minus 4AC, I'm going to get negative 7. So what does that mean? It could be an ellipse or a circle, right? And I don't know which one it is. Well, yeah, I do, because A is 2 and C is 2, and when they're the same, isn't that a circle? Well, that was true with the old classification system when I didn't have a B term. It is not true here. As a matter of fact, we mentioned the only way that you would know what this is to graph it. And so if you'll notice there in the textbook on example 4A, they do graph it, and it's not a circle, it's an ellipse. So I don't have a way to determine that other than graphing it. So I'm literally going to leave my answer ellipse or circle. All right, look at the next one. What is A? 1. What is B? Negative 6. And what is C? Positive 9. So if we do B squared minus 4AC, we're going to get 0. So what is this one? Parabola. Now, we mentioned when we learned the first classification system that in this section, we were going to be solving systems and graphing systems, and it would just be nice to know what it was I was working with before I started, trying to graph it or complete the square or whatever. And so now we'll have a classification system that will work whichever of those two types of equations I might have. Now, we have solved systems of quadratic equations before on page 728. They ask us to do it again. How come we're doing it again? Well, we didn't know how to do ellipses and hyperbolas when we did it before. So they want to revisit the topic and include those types of general second degree quadratics as well. So we look at example number 5, and we've got two equations here, and they asked me to solve this system. Now, we've got 3 ways that we can solve this type of a system. We can solve by substitution, we can solve by elimination sometimes, and we can solve by graphing. Why do I say solve by elimination sometimes? Well, let's say that in this equation, instead of just having x squared plus y squared minus 16x, what if I had another value in here like plus 5y? All right, I might be able to get these y's to drop out right here, but then there's not anything to cancel out over here with the 5y. Or what if I have something else in that bottom equation like a 3y? There's no way to get a coefficient that will make the 3 and the 5 drop out without getting it to mess up the plus 1 and minus 1 that I've already got over here. So even though elimination might be our favorite method, it's not always going to work. So that's why we might need to fall back on graphing or fall back on substitution. All right. So for this one, we'll solve by elimination, and then we'll also go back and solve by graphing so that we have a fallback. So if I go through and I combine, I am going to be able to get my y values to eliminate, and I'll be left with 2x squared minus 16x plus 30. I could divide both sides by 2 so that I had smaller values to work with. It's like taking out a common factor of 2 and dividing by it. And the quadratic that I'm left with, they were nice enough to give me one that would factor. So I'll get x equals 5 and x equals 3. Now, once I know x, I'm going to plug back in to find y, right? So in looking at those two equations, that second equation looks a whole lot easier to me. So I'm going to take 5, and I'm going to plug it back into that second equation. That was x squared minus y squared minus 9. So let's put 5 in the place of x. So I'll have 25. 25 minus 9 is going to give me 16. I'm going to move my y squared to the other side. And then take the square root of both sides. And when I get two different answers for y, that means that when x is equal to 5, y is equal to 4. And when x is equal to 5, y is also equal to negative 4. So that's two completely different ordered pairs. So both of those will be solutions. We also have that x equals 3 that was up here, right? So we need to plug that one in as well. So let's go through and plug 3 in. And again, I'm going to plug it into that second equation because it was simpler. So again, it was x squared minus y squared minus 9. So we've put 3 in the place of x. The 9's are going to drop out, and that would leave me with negative y squared is equal to 0. Divide both sides by negative 1, and I'll have y squared is equal to 0. And then take the square root of both sides, and I'll get plus or minus 0. Plus 0 minus 0, same thing. So I'm just going to get one ordered pair there of 3 zeros. So those would be my 3 solutions if I solved it algebraically. Now typically they're going to tell me to solve it algebraically and check it graphically, or solve it graphically and check it algebraically. So let's look at how we can do that. If I'm going to graph this, I'm not making a humongous XY chart. If I'm going to graph this, then I'm going to put it in standard form, which is really great practice for us in getting ready for our quiz and test this week. So before I put something in standard form and try and graph it, I'd really like to know what it is that I'm trying to work with. So for that first one up there, I do not have a B term. So I'm going to go back to our first classification system. When I don't have a B term, I look at A and C, right? So in this case, A is 1 and C is 1. So what type of a conic is this? It's a circle, right. And in the second one, A is 1 and C is negative 1. So what type of conic is that? When it's negative? Hyperbola, yes. All right, so let's start with that first equation up there. If that's supposed to be the equation of a circle, I have some work to do, right? Definitely going to need to complete the square. So I'm going to collect all of my x terms and leave room to complete the square. Collect all my y terms and move my constant to the other side. So to complete the square, I take the coefficient of the middle term, negative 16, cut it in half, so that's -8, and square it, that's +64, and I'm going to add that to both sides. So I've created this perfect square right here, x minus 8 squared, and then these constants combine to be 25. Now we know the equation of a circle is x minus 8 squared plus y minus k squared is equal to r squared. So that means I have a circle with a radius of a center of 8, 0, and a radius of 5. So I'm going to come down here to 8, 0, and I'm going to go up 5, down 5, right 5, and left 5, and draw my circle. So absolutely nothing new about that, but just good review for us. All right, for the second one, I had x squared minus y squared minus 9, and I know that's going to be a hyperbola. So in a hyperbola, when I move that constant to the other side, I know in standard form it has to be set equal to 1. So I'm going to go through and divide both sides of that by 9, and now I've got it in standard form. So I know my major axis is the positive one, A is 3, and B is 3. So I'm going to have a center of 0, 0 since nothing's being subtracted from either of those. So I'll start at 0, 0, go up 3, down 3, right 3, left 3, and draw my box. And the diagonals are going to be my asymptotes. Then I'll start at my vertex, and I'll draw this so that I approach those asymptotes. So there's the graph of my hyperbola. So I'm looking for, is it possible that I have solutions of 5, 4, 5, -4, and 3, 0? So sure enough, 3, 0 was my vertex, and it was one of the endpoints of the diameter here, so that's a definite. And then it looks very logical that 5, 4 could be a point of tangency for that hyperbola along the circle, and 5, -4 the same thing. So graphically, what I got backs up what I found algebraically. Now, if I did not want to complete the square, all right, I've told you that for this test you can use your graphing calculator. So if you're thinking, if I have to graph this, I'm just throwing it in my calculator. Well, if you don't want to complete the square and get it in standard form, how are you going to put something like this in your calculator? I mean, how do you solve for y? Because you've got a y squared here and you've got a singular y there. How do you do that? There is a way to do that, but it's a little bit of an extensive process. It's actually there in your textbook in example number 4. We're not going to go through that together, but if you'd like to play around with that, you're welcome to. Otherwise, to graph this, if you're not using method 4, to graph this, you're going to have to put it in standard form and use that Conics app on your calculator to graph it, or you're going to have to put it in standard form and graph it by hand. Okay? Now, for your homework tonight, on 29 through 35, you're just using the classification system. But when you get down to 41 and 43, and it says to graph it, you can graph it on your calculator if you play around with that method of example number 4, or you have to graph it by hand. I don't care which way you do it, there has to be a graph on your paper to get credit. You can't come in with just the answer written down out of the back of the book and say, well, I did it on my calculator. You have to graph it. If you're going to graph it on your calculator, that's fine, but that graph needs to be copied onto your paper. Okay? So in either case, I have to see the graph on your paper for you to get full credit.